So I want to walk you through a sequential design process from the start to the finish. And the start would be a plain language description of a problem to solve. So in this case, the problem is an elevator has 4 floors and can be called to any floor, but must proceed through intermediate floors before reaching the destination. And your job would be to design a sequential circuit that would implement the state machine for this elevator controller. So we start by saying, what are the states of this device and what inputs might be used to cause the state to change? Well, if there are 4 floors, then there are 4 possible states, which means we need the log base 2 of that for the number of state variables. So we can say that there are 4 floors, and we maybe list them as, the ground floor, floor 1, floor 2, and floor 3. And then these are going to be enumerated by the 2 state variables that we're going to use to describe them. So the ground floor could be state 0, 0. First floor could be state 0, 1, 1, 0, and 1, 1. 2 state variables and 4 possibilities. Now, we're also going to need some inputs. The inputs are going to ask for the elevator to go to one of the floors. So similarly, we're going to have 2 bits of input. And these are also going to be, so go to the ground floor. So this is the states. And these are the inputs. Go to the ground floor, go to the first floor, go to the second floor, go to the third floor. This seems fairly straightforward, but you'll see the little sort of hitch in this is that you can't go straight from the ground floor to floor 2. You have to go from the ground floor to floor 1. So if I ask the elevator to go to floor 2, then if it's in the ground floor, its first thing to do is to go to floor 1, and then it can go to floor 2. So that's the state machine that we have to build. So what we're going to do is we're going to draw out the state transition diagram. We're going to have these 4 states, and we're going to draw them out. 0, 0 for the ground floor. We're going to have 0, 1 for the first floor, 1, 0 for the second floor, and 1, 1 for the third floor. And then we're going to draw out our transitions. Now, if there are 2 inputs, that means there are 4 required transitions out of every state. If I'm in state 0 and the input is 0, if I'm in state 0 and the input is 1, if I'm in state 0 and the input is 2, and if I'm in state 0 and the input is 3. Now, we're not going to have any outputs for this device. The state is the output. But what we're going to do is a little bit of shorthand for these transitions, because drawing 4 transitions out of each state will make a very messy diagram. But you'll see how this will go. So first thing we can do is say, if I'm on the ground floor and ground floor is requested, then I stay on the ground floor. And that will happen for every state. If I'm on floor 1 and I request floor 1, if I'm at floor 3 and I request floor 3, if I'm at floor 2 and I request floor 2. So those are pretty straightforward to implement. Now, if I'm on the ground floor and I want to go to floor 1, then I just go to floor 1. But if I'm on the ground floor and I want to go to floor 2, I can't go straight to floor 2. I can't teleport halfway across the building. I have to go to floor 1 first and then go to floor 2. So this is, if I ask for a 2, I'm going here and then here, which makes sense because if I'm in floor 1 and I ask for a floor 2, that's where I go. In fact, if I'm on floor 0 and I request floor 3, the same thing happens. I go to floor 1. That's the only thing that I can do, really. Now, if I'm so this is 4 outputs, 4 outgoing states from state 0, ground, 1, 2, 3. What about from state 1? Well, if I'm in state 1 and I ask for the ground floor, I go back to the ground floor. That's easy. If I ask for state 1, that's here. Ask for 2, and in fact, if I ask for 3, in both of those cases, I have to go to state 2 because I can't teleport from state 1 to state 3 or from floor 1 to floor 3. And similarly, if I'm on floor 2 and I'm asked for floor 1, for floor of the ground floor or floor 1, then I go from 2 to 1. And then if I'm on the second floor and I ask for the third floor, I go there, and that is 1, 2, 3, 4 outputs from here. And if I'm on the third floor and I ask for any other floor, 2, 1, or ground, then I'm going to go back to the second floor. So you can see how this idea proceeds. Regardless of where I am, I can be on a particular floor, and there can be a request for a different floor or the same floor, and I will proceed through the states sequentially, ground 1, 2, 3, 3, 1, 2, ground, until I get to the floor that was requested. Now, we need to build a machine that will implement this finite state machine state transition diagram. So the next thing we're going to do is we're going to write this out in a different format, which is going to be the state table. I'm going to look at all of the possibilities for the current state and the inputs, and then we're going to write out what the next state will be for those possibilities. I don't know if I have enough room on this page or not. I better start a new page. So the current state of this machine, there are two state variables. We're going to call them Q1 and Q0 for the current state of the machine, or the floor that we're on. And then I'm going to have F1 and F0 as our inputs that are the requested floor. So this is our states, and this is the requested floor. And then as outputs from this table, I'm going to have the new floor. State variables. Now this is going to be 4 inputs, right? If I'm in state 0 and I have an input of 0, 1, 2, and 3. If I'm in state 1 and I have an input of 0, 1, 2, and 3, etc. So I'm going to write all that out. And this is your process as well when you do this. So you can do this on a computer, but I'm going to write this all out. And it'll take a minute. So if I'm in state 0, I have 4 possibilities. If I'm in state 1, I have 4 possibilities. If I'm in state 2, there are 4 possibilities. And if I'm in state 3, there are 4 possibilities. And you should recognize this as just an enumeration of the minterms for a 4-variable map, which makes sense. This is minterm 0, and this is minterm 15, because this process that we're following is to design the combinational logic that will drive the next state of the machine, which means we're driving combinational logic. That combinational logic will take as input the current state and the inputs. So 2 current state variables, 2 input variables, 4 variables. The combinational logic doesn't care if they're current states or inputs. They are the 4 inputs, and therefore the 16 minterms for a regular 4-variable map. And now what we have to do is take our state diagram, and we have to write out onto the state table what the next state will be for any given state. So some of these we can do. If the request is the same as the state that I'm on, then in those cases nothing happens. That's fairly easy. Then we can say that if I'm in state 0, then regardless of the input, as long as it doesn't say stay in the same place, I will go to state 1. So my next state is always going to be state 1. Now if I'm in state 1, we draw this stuff out. If I get a 0, I go back to 0. If I get a 1, I stay in state 1. But if I get a 2 or a 3, I go to state 2. Then, if I'm in state 2, if I get a 0 or a 1, I go to state 1. If I get a 2, I stay in state 2. And if I get a 3, I go to state 3. Then, for the last ones, if I'm in state 3, if I get a 3, I stay in state 3. Otherwise, I go back to state 2. So this is the next state for each state variable given the current state and the input. Now there are 2 ways to proceed from here. We have to choose which flip-flop we're going to use. I'm going to do both, and you can see then the comparison between the simplicity of the design process for D flip-flops and the simplicity of the end result for JK flip-flops. So first, if we want to use D flip-flops, A D flip-flop, remember, has a single input D and a single state variable Q. It has a clock and often has Q prime as well. But basically, for the D flip-flop, you present at its input the value you want it to store, which means these are already the inputs for the D flip-flops. So if I want a D flip-flop that'll store the next state, this is the input. If I want a D flip-flop that'll store the next state, this is the input. So I can make two K-maps with these existing numbers. These are going to be 4 variable K-maps. They're going to look like this. They're going to have the states down one side, Q1, Q0. They're going to have the inputs F1 and F0 along the top. And they're going to look like a K-map looks. And it's worth practicing writing this out because it's the kind of thing you'll need to do in the test, for one thing. But also, it's good practice for being able to develop these things yourself. Not forgetting to flip those last 2 rows. And then we can just read down these numbers and fill them in. 0, 0, 0, 0. That's the first row. Second row is 0, 0, 1, 1. Third row is 0, 0, 1, 1. And the last row is 1, 1, 1, 1. The order of putting them in is important to recognize. And then we can make our groups. There's a group there, and there's a group here, and there's a group here. And the end result then is, if we read it off of this K-map, the next state, or the D input, D1, is going to be equal to Q1, Q0, or it's Q1, F1, or it's Q0, F1. F0 doesn't even enter into this particular function. I think that's right. Let's double check. Q1, Q0, that's this group here. Q1 is here, and F1 is, oh, no, I did it wrong. These are F0s. Q1, F0. Oh, no, that's right. F1 is here. This is F1. These two are F1. So that's correct as the first time. F1, and then Q0, F1. So those are the 3 AND terms that make up the input to this flip-flop as a function of the current state of it and its partner flip-flop and the 2 inputs. And let's do the second one for consistency. And if you are good at drawing these out, you can just write them out, or you might want to use a ruler. And then again, Q1, Q0, F1, F0, 0, 0, 0, 1, 1, 1, 0. And again, you're going to read down this column, 0, 1, 1, 1, 0, 1, 0, 0, 1, 1, 0, 1, and then 0, 0, 0, 1. And those are the values of the K-maps for this one. Now, we're going to, again, group. There's a group here. And there's that's prime. This one here is prime. I'm going to draw those together because it'll turn out those actually can be simplified further with exclusive ORs. It's a checkerboard pattern, and these also end up being a checkerboard pattern. I'll complete the derivation because it's worth looking at, but you can see it's a little bit of work. So first of all, it's going to be Q0 bar for the pink group. This is the input for the 0 state flip-flop, is going to be Q0 bar, Q0 bar F0, and then the blue ones are going to be Q1 bar, F1 bar, F0, or Q1, F1, F0. And you can already see how that's going to give us a exclusive OR. I'll leave a space for that one. Or Q1, Q0 bar, F1 bar, or, and then this one here is Q1 bar, Q0 bar, F1. And if we take these two and select out the F0, we can say that this is the same as F0, and then Q1 exclusive NOR F1. And if we select out the Q0 here, Q0 bar, and then it's going to be Q1 exclusive OR with F1. So that's a lot of derivations. So the idea is simple. You don't have to do anything more here except to take this and implement it. But you can see the derivation is fairly expansive. So then let's draw out the circuit. We wanted a complete example. So the circuit looks like this. We're going to have a D flip-flop here. This is going to be D1 with the output Q1 and Q1 bar, because you get them both. And then another flip-flop here. This is going to be D0 with the output Q0 and Q0 bar. And then we're going to build input for the flip-flop D1, which is this function right here. It's going to be an OR gate with 3 AND gates. Oops. And it's going to be Q1, which comes from here, and Q0, which comes from here. And then it's going to be Q1 F1. So here's Q1 was here, and then F1, and Q0 F1. Here's Q0 F1. So that's the circuit for D1. D0 is a bit more involved. Again, there's going to be a OR gate, and that OR gate is going to have 3 terms, one of which is, these are going to be actually 3 ANDs again, and. The first AND is going to be Q0 prime F0. Now I could pull Q0 prime here, but it might be just easier to pull it from here and then invert it. And then F0 is here. And then these ones are going to be F0 and this exclusive NOR. So we'll put an exclusive NOR here. F0 here. And then this one is going to be Q0 bar and an exclusive OR. And what did we say? Q0 bar is here. So this is Q0. We'll put this through like this, and then we'll invert it. It's getting messy, right? And then this exclusive NOR is Q1 and F1. So here's F1. And then Q1 was this one, first one here. Let's bring that one out like that. And then this one is Q1 exclusive OR F1. There you go. So that's the full circuit for the D flip-flops. And if you implement this, we need to make sure that our clocks are connected. You will find the result as you would expect. Now, we're going to do the same derivation with JK flip-flops and see how a little bit of extra work will give you a much simpler circuit. So let's have a look at it. Given this, I'm going to actually start with another sheet of paper for the JK inputs. So first thing we're going to do is remind ourselves how a JK flip-flop works. We need the excitation table for the JK flip-flop. And that looks like this. We can have, if I'm in state Q and I want to be in state Q, what do I have to provide as J and K values to make that transition happen? Well, there's 4 possibilities. And again, if we remember the functionality of the JK flip-flop, if I'm in state 0 and I want to proceed to state 0, I have 2 options. I can either hold, which is 0, 0, or I can reset, which is 0, 1. So both of those will get us to a 0, right? Reset to a 0 ignores the current state, and hold persists the current state, or allows the current state to persist. Both of those will get us to a 0. If I'm in state 0, I want to go to state 1, I've got 2 options. I can either toggle or set. So J has to be 1, but K doesn't matter. 1, 1 for toggle, 1, 0 for set. Then again, if I'm in state 1 and I want to go to state 0, I can either toggle or reset. 1, 1 for toggle, 0, 1 for reset. And if I'm in state 1, I want to go to state 1, I can either hold or set, which is X and 0. 0, 0 for hold, 1, 0 for set. So this is my excitation table, and I'm going to use this a lot to figure out what the value for the JK inputs should be to make these state transitions happen. So if I go back to my original state transition table, and then I start to look at what values I need for each of these transitions, I can use the JK state transition table to figure that out. So now, if I say I want to figure out what J1 and K1 should be, and J0 and K0. So you can see already I'm going to need 4 functions. So it's going to be twice the work, twice as many K-maps, but the K-maps are going to be full of don't cares. We'll see how this works. So J1 is going to be, I'll do this for a couple of them just to make sure that the derivation is clear, and then we'll sort of rush through the rest of them. So these examples here, the pink one and the blue one, we'll look at. So in min-term 0, I'm in state 0 for Q1. I want to go to state 0 for Q1. That means if I'm in 0, I want to go to state 0, that's 0x for J and K. Because I can either flip, or I can either hold J, hold the current state, or I can reset the current state. That's 0 and x. Then, that's the same for Q0 and Q0 plus, 0 and x. 0 to 0 is 0 and x. And then if I look at the blue one, if I'm in state 0 but I want to go to state 1, that's 1x. And I could just proceed down the rest of them. These are all 0x, 0s to 0s, and then these are all 0s to 1s, so that's 1x. Now, for the second row. All of these are zeros, so 0 to 0, 0 to 0, that's 0x, 0x. 0 to 1 is 1x. And then, looking at Q0, 1 to 0 is x1, 1 to 1 is x0, 1 to 0 is x1, 1 to 0 is x1. Okay? Third row, 1 to 0, I'll go back to my table. 1 to 0 is x1, 1 to 0 is x1, 1 to 1 is x0, 1 to 1 is x0, and then for Q0, these are all zeros, so 0 to 1 is 1x, and 0 to 0 is 0x. Last row. So this takes a bit of time, but you can work it out. Last row, I'm always in state 1 for these two. 1 to 1 is always x0. And then 1 to 0 is x1. And the last one is 1 to 1, which is x0. Okay, so those are my 2 JK flip-flop inputs, each of which needs 2 inputs, 1 for J and 1 for K. And now we're going to make these 4 Karnaugh maps. So again, the inputs are Q1, Q0, F1 and F0. And I'll move this over so you can see it. Get this out of the way. Zero, 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 one, 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 zero. And because these are in min-term order, I don't even need to look at the inputs. I can just go down the row. 0, 0, 0, 0, 0, 0, 1, 1. And then, x, 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 x. Wow. So, although I have to do twice as many K-maps, the K-maps are significantly simpler. J1 is just equal to Q0, F1. Here's K1. And again, going down here, X, 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 then 1, 1, 0, 0, 0, 0, 0, 0. Super simple. Again, not going to spend all my time labeling it because we can see from here this is Q0 prime. So this is K1 equals Q0 prime. And then it is F1 prime. All right? Yeah. One more, two more. And we'll just go down the list. 1, 0, 0, 0. Oh, sorry. 0, 1, 1, 1, X, 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 X. And again, I'm just going down the list in the order of the midterms that are on the table. 1, 1, 0, 1, X, 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 X. I know it's a bit messier, but you get the idea. And we'll group right here, a nice big group. And what else can we see? There's actually two here. There's a group like this and a group like this. And if you're paying attention, you would see that these are actually an exclusive OR term as well. So this is J0 is just equal to F0, this stuff here. Let's label them again. Q1, Q0, F1, F0. And so this big middle one is going to just be F0. That's all it is. Everything else changes. Or, and then this is Q1, F0 prime. Sorry, F1 prime. Right, F1 prime. Or Q1 prime, F1. Which is the same as F0 or Q1 exclusive or F1. Super simple compared to the significant mess that was the D flip-flop inputs. Now we can see why we would choose JKs. And really it's your choice unless I tell you to do otherwise. Here's the last one. And again, I'll just read it off down here. So it's X's and then 1, 0, 1, 1. X, 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 1, 0, 1, 1. And then it's X's and 1, 1, 1, 0. X, 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 1, 1, 1, 0. Pretty. And again, we've got a group here and a group here. It looks very familiar. In fact, that's the same term. Now we just use this as the opposite. So this term here is shared. And so I don't have a lot of room on the end of this page, but K0 is this big term here, which is F0 prime, or Q1 exclusive, or F1. And we can draw the entire figure, just like we did for the D flip-flop. We can do the same thing for the JK flip-flop. Each of these flip-flops has two inputs, J and K. This is the one for the 1, and this is a Q1 output. And then another one, J0, K0, Q0. And there would be a clock that would be shared. So J1 is just Q0, F1. Q0, F1. F0 here, oops. Like that. Q0, F1. K1 is Q0 prime, F1 prime. So Q0 prime, F1 prime. Q0 prime, F1 prime. That makes sense. And again, we could pull Q0 prime from here because we usually have it. But in this case, we'll just use an inverter here because it's simpler to look at. Then J0 is going to be F0 or an exclusive OR. So we need an OR first, and then F0, and then an exclusive OR here. and the exclusive OR is Q1, F1. So here's F1, and you need Q1 to come around now. So we'll bring Q1 around like this, Q1, F1, and that, again, we saw was actually shared between those two terms. It's the same exclusive OR term for both of those. And this one is ORed with F0. This is ORed with F0 prime. So F0 prime, and we're done. So that is the circuit for the JK implementation. And I'll compare it to the circuit for the D implementation. And you can see that and this is pretty typical, the D implementation has more complicated circuitry, but you only have to build 2 of them. The JK has significantly simpler circuitry, but you have to build 4 of them. So that's really the toss-up, the question that you decide when you are deciding which of these to do. So that's a complete derivation from a problem description to a finite state machine map to a state transition table, a state transition table, which can go straight to D flip-flops, or into JK flip-flops using the JK excitation table into the JK circuit. And then after this, what you would do is you would implement this in your logic design software. You would run simulations to verify that the circuit behaved as you expected to behave, and then you would write this out in a neat and tidy way. This is a little bit messy to hand in, but it's close. And you would have your final solution.